When an AI reads text, it's playing a guessing game. Each moment it asks, what comes next? Guess correctly and the cost is low. Guess wrong and the cost is high. That cost has a unit. It's measured in bits, and it was invented in 1948. His name was Claude Shannon, and his equation is the reason every AI in the world can write, translate, code, and think. This is information theory. How surprised are you when it rains in the desert? Now imagine measuring that surprise with exact numbers. This is the formula. I of x equals negative log base 2 of p of x. When an event is likely, surprise is low. But as the probability drops, surprise shoots up. A fair coin flip? Exactly 1 bit of surprise. A 1 in 100 event? 6.64 bits. Claude Shannon asked a deeper question. What is the average surprise? This curve is the answer. Binary entropy. At p equals 0.5, maximum uncertainty, exactly 1 bit. But bias the coin to 90% heads, and entropy drops to 0.47. At 99%, almost zero surprise. The outcome is nearly certain. In 1951, Shannon measured the entropy of English itself. If every letter were equally likely, 4.76 bits per character. Add letter frequencies, it drops to 4.03. Add digrams and trigrams, 3.32. Add word-level patterns, 2.14. And when humans predict using all their knowledge of language, Shannon found the answer is about 1 bit per character. That is the true uncertainty of English. If entropy measures reality's uncertainty, cross-entropy measures how wrong your model is. In episode 5, we used this loss function. Now we finally see where it comes from and why no other loss function makes sense. Here is the true distribution. Word A appears 70% of the time, B 20%, C 10%. The entropy of this distribution is 1.1568 bits. That is the theoretical floor. No model can do better. Now let us test 4 models against this truth. The perfect model matches the true distribution exactly. Its cross-entropy equals the entropy 1.1568 bits. A good model is slightly off, 1.1896 bits, just a tiny penalty. A medium model spreads its bets too evenly, 1.4464 bits. And a bad model? It puts 70% on the wrong answer, 2.8412 bits, more than double the floor. Every bit above the floor is wasted. That extra cost has a name. It is the KL divergence. Cross-entropy equals entropy plus KL divergence. The floor plus the penalty. The perfect model pays 0 penalty. The good model, 0.03. The bad model, 1.68 bits of pure waste. Remember the loss landscape from episode 7? The deepest valley is the entropy of language itself. KL divergence is the tax on being wrong. It measures every extra bit your model wastes. dKL of P and Q equals the sum of P of X times log of P over Q. Here, the true distribution in gold, the model in green. The gaps between the bars, that is the divergence. For this good model, the KL divergence is just 0.03 bits. Now watch what happens as the model improves. The green bars move toward the gold, the gap shrinks, and when they match perfectly, the KL divergence hits 0, no wasted bits. And this tax is not fair. dKL from P to Q is 0.0328, but reverse the direction dKL from Q to P is 0.0348. They are not equal. KL divergence is not a true distance, it is asymmetric. Here's the full picture. Cross-entropy equals entropy plus KL divergence. The floor you cannot beat plus the penalty for being wrong. 1.1896 equals 1.1568 plus 0.0328. Perplexity is one number that tells you everything. Is your model smart or is it lost? 2 to the power of cross-entropy. It is the effective vocabulary size. A perplexity of 20 means the model is choosing uniformly among 20 words. Our perfect model has a perplexity of 2.23, choosing among just 2 words. The bad model, 7.17. It is lost among 7 possibilities. Imagine a roulette wheel of possible next words. In 2000, the best models were choosing among 141 words, a huge, confused wheel. By 2020, GPT-3 had shrunk it to just 20, 7 times more focused in 20 years. Here's the scoreboard, the Penn Treebank benchmark. In 2000, a simple trigram model scored 141. By 2014, LSTMs brought it down to 78. ADLSTM hit 57 in 2017. Then GPT-2, zero shot, 35.76, and GPT-3, 20.5, from 141 to 20 in 20 years. Here's the deepest insight in all of AI. Predicting the next word and compressing a file are the same math. On the left, a file shrinks as patterns are found. On the right, a model predicts each word. Every correct prediction is bytes saved. Every wrong prediction is bytes wasted. Compression and prediction are two views of the same equation. In 2024, researchers proved this is not just theory. Chinchilla, a 70 billion parameter model trained only on text, compressed images to 43.4%. PNG, the dedicated image format, 58.5%. It compressed audio to 16.4%. FLAC, the dedicated audio codec, 30%. A model that has never seen a single image or heard a single sound compresses them better than purpose-built tools. This idea is so powerful that there is a prize for it, the Hutter Prize. 500,000 euros for compressing 1 gigabyte of Wikipedia as small as possible. The current record, 0.91 bits per byte, nearly at the theoretical limit. Better prediction means better compression, which means smarter AI. They are all the same problem. Mutual information answers the ultimate question. How much does knowing this tell you about that? I of x semicolon y equals h of x minus h of x given y. Picture two circles. The left is everything uncertain about x, the right, everything uncertain about y. The overlap is mutual information, 0.2781 bits. That is how much x and y share. The total joint entropy is 1.7219 bits. Left only plus overlap plus right only. Here is the joint distribution. When x and y agree, probability is high, 0.4. When they disagree, probability is low, 0.1. We can cross-check. H of x plus h of y minus h of x comma y gives us 0.2781. The same answer. Mutual information connects everything we have learned. Remember vectors from episode 1? A probability distribution is a vector that sums to 1. Bayes' theorem from episode 3 is an entropy-reducing machine. Each observation squeezes out uncertainty. And the embedding spaces of episode 10 succeed when they maximize mutual information. Keep the signal, discard the noise. Claude Shannon, born 1916 in Petoskey, Michigan. He rode a unicycle through the hallways of Bell Labs. He built a maze-solving mouse from 90 telephone relays. He wrote a mathematical theory of juggling. He was a distant relative of Thomas Edison, and his work inspired David Huffman, who invented optimal coding as a term paper for a class at MIT in 1952. Here's the arc, 75 years of the same math. In 1877, Boltzmann gave entropy to physics. In 1928, Hartley separated information from meaning. Then in 1948, Shannon gave it all a formula. From neural language models to GPT-3's Perplexity of 20 to the proof that language modeling is compression, the math has not changed one bit. From 1948's coin flip to GPT, 75 years. The math has not changed one bit. Well, exactly one bit. Let us recap the 5 ideas from this episode. First, Shannon entropy. Uncertainty has a number, measured in bits. Second, cross-entropy, the score that tells you how wrong your model is. Third, KL divergence, the asymmetric tax on imperfect predictions. Fourth, perplexity, from 141 to 20 in 20 years. And fifth, the deepest insight, predicting and compressing are the same math. 11 episodes, from vectors and matrices through gradient descent, Bayes' theorem, backpropagation, softmax, universal approximation, loss landscapes, convolution, SVD, and embedding spaces to information theory. Each episode builds on the last. Each concept connects to every other. And next time, we ask the question that changed everything. How does AI learn to focus? The attention mechanism. Attention weights are probability distributions. Their entropy tells you whether AI is focused or confused. That's next time on The Math Behind AI.